Differentiation allows us to determine how a function changes around a point. Now we can see how this allows us to approximate a function using derivatives. And also we have seen that in order to compute derivatives, we can use some derivation rules. Since these rules are sort of algorithmics, then we can let the computers do their thing and compute the derivation themselves. But let's start to how we can approximate derivatives and the differentiation. So let's take a smooth function f. By smooth we mean that we can differentiate this function f n times. We define then the Taylor polynomial of degree n that we will denote by Tn. This Tn, the Taylor polynomial of degree n, is equal to the sum of these terms. We take the ith derivative, the sum between e equals to 0 to n of f, the ith derivative of f with respect to x0 over the factorial of I multiplied by x minus x0 to the power of I, which leads us, if we consider the polynomial of degree n, to f x0, f prime, the first derivative of f computed on x0 times x minus x0, so on, to get this term, the nth derivative of f computed on x0 over the factorial of n, and multiplied by x minus x0 to the power of n. This is the Taylor polynomial. We can then use the Taylor polynomial to state the Taylor theorem. And we say that this smooth function that can be derived n times can be approximated using this Taylor polynomial of degree n. In particular, we have that f, the function, with computed respect every point in A, is equal to the Taylor polynomial with respect to of degree n with respect to f and that point x, plus a residual term r n x. In particular, this residual term, this error, sort of error, is such that the limit, if we consider the limit of x that approaches x0, is equal to 0 if we compute n x over x minus x0 to the power of n, which means that this thing approaches 0 when x approaches x0. This thing approaches 0 faster than the denominator. In fact, this means that the closer x is to x0, the more the approximation is true. So f of x can be approximated by the Taylor polynomial of degree n. Let's see a geometric interpretation, and let's take this f equals to the sine of x plus the cosine of x. And in this straight line, in black straight line, we can see the function f, the result. And in the dotted lines represent the Taylor polynomial of degree 0, 1, 5, and 10. We can see that increasing the degree of the polynomial, the approximation becomes better and better. For example, with t equals to 0, the approximation is very poor, but with the Taylor polynomial of degree 10, the approximation is really good. So the greater is n, the bigger the neighborhood of x0 equals to 0 is, in which the polynomial, the Taylor polynomial of degree n approximates f very well. Again, we can, if the function is so smooth that it also can be differentiated how many times we want, then we can define the Taylor series, in which here we don't have n, but we have infinity. That's a series here. And if the function is so smooth that f of x is equal to the Taylor series, then the function is said to be analytic. Also, if x0 is equal to 0, and we are considering the approximation around 0, we are talking about the Maclaurin series. For example, in physics, we use a lot of these Taylor approximations, in particular the so-called small angle approximations. For example, we use the if we consider the function f as the sine of the angle, then the Taylor polynomial of degree 2 with respect to x0 equals to 0, then this is equal to the angle itself. In fact, when the theta is equal to 0, the sine is 0, and so the approximation is exact. If we move a little bit far from 0, then we get to this approximation. With the cosine, instead, we have the Taylor polynomial of degree 2 that is equal to 1 minus the angle to the power of 2 over 2. And these small angular approximations can be seen in these graphs. Here we didn't talk about the tangent, so let's not look at the blue line on the left plot. But as you can see here, we have x, which is the approximation, which is the angle, and the sine of x. As you can see in here, 0, we are considering 0, and the approximation is pretty good, but degrades when we go far from x0 equals to 0. Again, the same for the cosine, in which we have that the cosine of 0 is equal to 1. And then the approximation degrades, gets worse when we go far from x0 equals to 0. Okay, now we want to use the derivation rules to automate the computation of the derivatives. This involves especially the learning of a machine learning model, a machine learning algorithm. When we write a software that expresses some machine learning model, to train them, we will see that we will use differentiation. So we prefer, of course, to let the computer do the optimization, the differentiation. So differentiation, as we've seen, involves the application of mechanical operations, and we take advantage of it through automatic differentiations. So we can numerically evaluate the exact, note that we are talking about exact derivative, gradient, and so on, of a function by working with the intermediate variables and applying the chain rule. So if we have complex functions, we can work with intermediate variables and apply the chain rule to wrap it up altogether. For example, here we have this computation in which we start from x, our input. We compute a function that gives us a. Then, given a, we compute b, as here. And then from b we get our output. That's y. So these a and b are intermediate variables. We can express y through x immediately through the thanks to the composition of these three functions. But using the intermediate variables, the derivative can be expressed using the chain rule in this way. So we have the composition of 3,000 of functions is very difficult to compute, especially for a computer, but we can easily express them taking advantage of introducing intermediate variables that refer to every term that is used in the chain rule. In applying the chain rule, we can use two approaches. The first one is the reverse mode, the second one is the forward mode. Remember this graph, we go from x to a to b to y. In here, if we go from x to a as the last term, because we have already computed this one, we are going in reverse. We're going, okay, I compute y, b, this derivative, then I go back and I do b, a, okay, and so on. So I'm doing a reverse mode, what is called backpropagation. In the forward mode, instead, I look at in order as I do the computation and the composition itself. So I go from x to a to b to y. That's the forward mode. The reverse mode is very important. And in here you can see the application of the backpropagation considering an even more complex function, this one. And here we have our computational graph. And the backpropagations involve starting from the result f of x and taking every step and applying the backpropagation and the differentiation rules we've seen in the previous section. So this was a very fast looking about how we can use differentiation to approximate functions around a certain point, and how we can use computers to compute the differentiation themselves. In the next section, we will see instead the second subject about calculus, the integral calculus.